Hello, can everybody see the presentation?
Yes.
Okay.
Yep. Okay. Hello, everybody. Our project is autonomous navigation using centralized intelligence. Here's just a basic outline of what we'll be running through today. The motivation for our project, the related theories, our hardware and software designs, and then a demo video. Here's a picture of us, our team. We're going to introduce ourselves now. My name is Andrew Bunyan. I'm team leader, project manager, and hardware lead, and I'm most interested in control systems engineering.
My name is Michael Campilia. I'm the software lead and interested in machine learning and AI.
I'm Oscaro. I'm the hardware and software support, and I'm interested in database system.
I'm Jack Popovic. I'm the firmware lead, and I'm interested in hardware, software interfacing, and machine learning.
Okay, so let's begin with the project motivation. What motivated us to approach autonomous navigation is that self-driving cars are slowly gaining more and more traction and popularity in modern society. Currently, the standard global positioning system, GPS, will calculate the most optimal route from your current location to a destination location using path planning while considering satellite data on traffic, road speeds, and detours. However, it does not take advantage of any of the information that could be acquired by autonomous vehicle data and does not offer any communication between vehicles or infrastructure. To approach a solution, we first looked at how the big companies are going about their autonomous navigation projects. For instance, Google's autonomous vehicle uses a laser rangefinder to generate a 3D map of the environment, and it uses these maps to produce different types of data models to navigate. Amazon, on the other hand, uses a central network to monitor traffic flow and generate routing instructions for their autonomous delivery vehicles. After analyzing our options, we decided to fuse other companies' approaches. Our vehicle makes use of 3 different sensors: camera, ultrasonic, and infrared, and a database where all vehicles are sending their vehicle data to continuously pinpoint their location. Our ultimate goal was to create an autonomous vehicle navigation system with the intention to reduce traffic with optimized routing, increase overall driving safety with collision avoidance, and to make driving a more enjoyable experience. The level 0 of this functional decomposition shows the foundation of our project at its core. As you can see, our autonomous navigation system uses internal autonomous vehicle data such as speed, location, and orientation as an input. Additionally, it also takes the user's route request to output the most optimal route, as well as continuous confirmation that an action is safe to be made. Level 1 of the functional decomposition shows every module that makes up level 0. As shown by this diagram, the image recognition module, right here, takes in surrounding environments such as traffic signs, traffic lights, and other obstacles and processes this information and sends it to the database. The database then feeds this information to the convolutional neural network for behavioral cloning. Finally, the path planning and route calculation takes in each car steering angle and the rest of the process information to produce an optimal route.
All right, so there's many different aspects of computer vision and other related theory involved in this type of project. One important aspect would be lane detection, and this was completed using well-known techniques on OpenCV and Python. And as you can see in the flowchart, the first step would be reading a frame of video, and then the next thing would be pre-processing the image, and that would just be converting to grayscale or using a Gaussian kernel to reduce noise. Then we would perform canny edge detection, and you can see in those two equations, one of them is calculating the magnitude of gradients in the image, and then the other is calculating the angle of those gradients. After that, you would want to crop the image for a region of interest. So in our case, the region of interest would just be the road, so we would want to get rid of any part of the image that did not include just the road lines, so get rid of the background. And then finally, you would want to calculate hue lines, and you would use the equation on the bottom right to take the image onto a hue plane, and then calculate these gradients. And then finally, you would want to display the lane lines onto the original frame. Another important component was image recognition for object detection, and this was completed with OpenCV as well, and then TensorFlow on Python. And related theories for this included pre-processing the images, creating feature maps for the images, and then training convolutional neural network for the classification itself. So as you can see, just walking through the entire, all the steps, you would have the original image, you would pre-process it using a Gaussian kernel, and converting grayscale. Then next step would be creating feature maps. So there's two important steps to this. One would be actually convolving the image or going through the convolutional layer, and this takes a small square and runs through the entire image and then extracts the most important features using like mathematical functions. And then after that, you would want to do a pooling phase, and we use max pooling. And this is just a way in which the image is reduced in size while trying to maintain all of its most important details and features. And so in our network, which was a modified Linnet convolutional neural network model, and we ran through various convolutional pooling layers and then finally put it into a traditional neural network that had dense layers, and then came out with an output which was the class prediction, like such as a stop sign.
So this is our hardware implementation. So the first picture on this slide shows the overall placement of our sensors and our motors, and as well as the communication module that we use for our actual physical implementation of the vehicle itself. So the sensors are placed in such a way that they get the overall coverage of the vehicle on all sides and also in the back. This allows the vehicle to make the correct decisions and to accurately avoid other obstacles that could be found in the road. And our motor shield setup and motor locations. This is set up so our servo motor in the middle is controlling our camera and allowing it to spin, and the side motors are the ones that actually run the wheels. So they actually allow the vehicle to move forward and turn and do other navigation. And the motor, and so this is our, go ahead, next one. And so this is our track design itself. This is the track that we actually came up with in the end. It has a stoplight right there and a stop sign on the coming back after making the turn at the end of the track itself. And it's wired and controlled all through a microcontroller. So, and this is our hardware progress. As you can see, we started with a simple breadboard that allowed us to see the state of the actual breadboard based on the sensor inputs. So the LEDs would light up based on that state. And then we improved to the vehicle, but the vehicle did not have the neural network implemented on it and did not have a camera. And in our final hardware design, we actually included that camera on top, as you can see, and we also included the capabilities for wireless communication. Also, on top of that, all the sensors were functioning and were able to actually avoid vehicles in the road.
So for software design and implementation, we had a few components. We had first the MySQL database, which continually updated with inputs from the vehicle sensors. This included the car location, speed, acceleration, and steering direction, as well as image data from the camera sensor in the form of JPEGs. We also had the lane detection and object recognition, and as I mentioned earlier, it was using Gaussian kernel edge detection and a convolutional neural network. And then for the self-driving car, we would pre-process the image sensor data with OpenCV, and then we trained a behavioral cloning neural network with using simulators, including Udacity and Carla, to determine the correct steering angle and other components. And then using all of that data and path planning, we would calculate the correct optimal safe route and send it to the Arduino controller. For the object detection for traffic signs, this is just how we implemented it. We used a data set that had a variety of about 40 different traffic signs, and we fed that through our Linnet convolutional model, which you can see on the bottom left. And that's just, if you look closely, you can see the convolutional layers, the max pooling layer, and then finally the dense layer, and then an output layer. And that was trained using 10 epochs, which epochs is just like a set of training period. And over that training period, after that was done, we would feed it a completely new image that is never seen before, and we would see the predicted sign that it gave. And we'll talk about the results later. And then for the behavioral cloning, what we did was we would use the simulator or a camera sensor image. So as you can see on the top left, that would be the original image. Then we would pre-process it, and we would use a specific color scale. It was like a YUV color scale, and this was for our NVIDIA neural network model, which is good for autonomous vehicle training. The training set that you can see in the graph is the examples of steering angles that were given, and we obviously want we want more straight line or like straight zero steering angles, because obviously a car is going to be driving straight more than it turns. We run it through the model, and then we had to create another script that would actually send the control to the vehicle, and that was using sockets and socket IO, and then loading the train model and then sending it to the simulation and to the car itself, and it would send the steering angle and the speed.
So as Jack described before, our car is made up of ultrasonic sensors, infrared sensors, a camera, and a line tracking sensor to stay on the road. The controller we use is an Arduino, and it was connected to the RC controller by simple transistor switch circuits, where each individual pin from the Arduino directs which direction the car will be going. The Arduino would send out a high or low depending on the received serial message from our Python script. And this was just one of many ways and different methods that we use to control the controller with the Arduino. So simple iterations of our hardware design. We started off, as you saw in the first picture, with just a breadboard, testing out the ultrasonic and infrared sensors to simulate the object detection in front of the board. We then built the RC car chassis with sensors built in, pointing forward, left, right, and then behind. And then adding the four wheels with the servo motors. A lot of testing was done with the servo motors, making sure that they were the right speed and the right direction. We then built a simple versatile track that we were able to modify anytime, so that we could test the car and then modify, test again, and keep debugging. And lastly, we placed a camera sensor and Ethernet shield to actually implement our neural network and decision-making capabilities. And this is all further explored just through this table. This was a breakdown of when we did everything, when we tested the sensors, the ultrasonic sensor, IR sensor, our motors, making sure that they were tested properly with the right voltages and went to the right speeds. And obviously this took multiple iterations, and here's more towards the end of our project where we were focused on integrating everything and having proper decision-making tools. So as you can see, it took more iterations for decision-making, since that is the greatest part of our project, is the ability for the car to know where to go and when to go and make sure that is correct.
So these are just some of the object detection algorithm testing and results. So this was tested on a training set and a validation set, and then finally a test set. These graphs show the loss and the accuracy of our convolution neural network model. And as you can see, what you want generally you want a low loss and a high accuracy, and you always want the validation accuracy and validation to be higher than the training accuracy, and the validation loss to be lower than the training loss, because if the training accuracy is too high, then that means it would overfit the model, and you don't want that, because you want to be able to generalize to different conditions. And so in this case, this was good because our validation's accuracy was higher than the training accuracy, and we ended up getting a test accuracy on the test set of about 97.3%, which is pretty good.
This chart is a demonstration of 5,000 iterations that we have went through. Using the simulation software aforementioned, Carla, we provided the simulated vehicle a route from point A to point B. Every time the vehicle made a mistake, as seen by the labels on the y-axis here, such as misidentifying an obstacle, misidentifying a road sign, if it didn't stop at a stop sign, if it passed over a lane, or if the vehicle crashed, the script would reset and a new iteration would start. As you can see, we were able to successfully complete the route 94% of the time.
So this is a basic one of our unit tests. We had many unit tests because of all the components that we used on our actual project. So for this test, all we did was we calibrated the infrared sensor, and to do that, we connected the infrared sensor to a 5 volts power supply, and then monitored the output on an oscilloscope, and this allowed us to see how the sensor would actually react when we moved an object in front of it, and it allowed us to calculate the distance that the actual sensor was actually going to send the signal to make the decision. And if you go to the next slide, This is just another one. I'm not going to talk about it. We did the same thing, but we did it with the ultrasonic sensor in this case. And then these are some of the technical challenges that we faced and some of the things that we had to take direct corrective actions on. So for the sensor calibration, like I said, we used the oscilloscope to calibrate it to the exact distance that we wanted the sensor to react. And we added the ultrasonic sensor for in case that there was low visibility situations. This allows us to scale our vehicle up to the real world and to actually use our vehicle in the real world. We in order to fix some of the logic issues that we had, we just changed the logic and integrated more sensors into our actual vehicle. And we decided to change the neural network architecture from reinforcement DQ learning to supervised behavioral cloning. This allowed for a better decision making overall, increased the accuracy and efficiency of the neural network, and we tuned the hyperparameters of the network to produce more accurate results.
So this right here is the demonstration video. The first part is just would be showcasing the lane detection. This is just a video feed with no lane detection right now. This is just how a normal video feed, and then we will run a script. And now you can see, if you can see the purple lines, that is real-time detecting the lanes. And then this is our behavioral cloning model in working in action with the script I mentioned earlier, sending the actual controls to the car and to the vehicle. And this is just like really like every millisecond is sending a steering angle, and then right here is how the car is actually driving based off those steering angle and the speed and throttle. And coming up in the simulation, you can see a stoplight, which is red, so this car stops. And then once it turns green, it will continue going and turn. And basically, it maintains the speed limit that it can see through road signs.
Yep.
And then this is the hardware demonstration.
Yeah, so as you see in the hardware demonstration, there is a little bit of lag when it tells us to go past the green light. That's because of the overall lag and latency issues in our network, but we weren't able to actually fix them. But as you see, it stops at the stop sign and also stops at the red light based on the camera input.
And so here's just the cost analysis, our entire bill of materials. As discussed, all of the hardware components, our sensors, our microcontroller, the camera and module, everything together ended up being $184, which was considerably lower than our budget for the project. Here's just the project timeline that we set out in the very beginning of our project that we followed pretty well, starting with a lot of research and gathering of materials, some construction of the track and developing of our network, and then training and testing of our network, and actually putting all together and integrating and testing and debugging up to the very end.
At this point, we have successfully achieved our goal in a simulated setting. Our objective has changed due to the circumstances, and as a result, we will be looking to improve everything we have achieved physically at a future time. The functionalities of our automated vehicle are to correctly calculate the most efficient route, to be able to process and identify different traffic signs, and to continuously find the most efficient and safe decision. We have taken multiple codes and standards when approaching our project. For example, the 1968 Vienna Convention on Road Traffic states that an autonomous vehicle should never be fully autonomous and should always allow the user/driver to take charge at any point. Additionally, we have taken database standards, communication standards, V2I standards, and autonomous vehicle safety standards into account.
In our project, the field that we're pushing here is facing a lot of ethical issues, specifically in terms of safety. So we hold paramount the safety and health and welfare of our users of our product, of the public. Us as creators of our project, we are determined to be honest and realistic in our claims, not to falsify or fabricate any data or anything that we put out to the public. We want to make sure that we uphold the highest competency and undertake and push for better results and more accuracy, and to take honest feedback and criticism of our work. Here's just our references of everything that we used. Are there any questions?
Yes, I have a question, Andrew. Can you show me the At the early beginning, you saw a diagram with the training data, a histogram. You saw a histogram of the training data. Can you go back, please?
Yeah,
Yes, no
Oscar, we'll go
problem.
back here.
Are you referring to this?
No. It's the training data of the steering angles.
Oh, is that the
There.
video?
Yeah.
No,
Oh,
that.
sorry.
Yeah.
We're
Yes.
cloning. Yep.
Yes.
Yes.
What are you planning? What significance they have this data in the project?
The steering angles.
Yeah, the steering
This
angles. Yes.
data was used in the neural network for the behavioral cloning aspect of the vehicle. So basically, it would have the steering angle and then also the images in order to uh, train the network so that you could provide it an image and then the model would be able to give you it the correct or like what it thinks the steering angle of the car should be.
Uh, how did you take this training data?
How did we take the training data? We
Yeah,
used a simulator basically that
I
is
see. I see. Are
that would
from
let you
simulate.
record a bunch of a video of a car driving correctly, and then it would take down the images as well as the steering angle.
So it's a simulator, okay? What
Yes,
represents this extreme data that you have right and left? You see data with higher pulse PDF. Why, how comes this?
you are you talking about the negative one and the one at the end at the
Yeah,
sides?
the PDF yeah, is higher. Why?
Those are just for full
Normal,
turn. Uh,
are normalized data or why the
the data
values are higher here, left and right?
the values are higher for the full turns for left and right when it's completing a like a full 90-degree turn.
This is for 90 degrees, correct?
Yeah, like for yeah.
What kind of function is if you feed the data in a function? What kind of function is this?
What what do you mean? What kind of function?
Did you feed this histogram on a function to identify if it's
This
Gaussian, if it's binomial, if it's whatever it is?
oh I mean I believe this would be Gaussian for the most part. This it's a little non-Gaussian for the data set, but this was just used as one of the inputs to the model for determining
Yeah, it's nice to plot this data to find out what curve they represent. You know,
yeah, that's a
if you
good
know the curve, you can get more meaningful information. You can kick out some of the data that you find that doesn't make sense.
yeah, that's a good idea.
And you can also, okay, do you know why you're using this histogram here as a training set? Why you choose histogram?
No, it's not. I just created it into a histogram for visualization of the training set.
Okay, because this histogram, if you can put it as a training set, this reduces also the number of data.
Yeah. Oh, that is true. If we used it
And
as a.
reduce the number of understand
Mhm.
what I mean?
Yeah, I understand what you mean.
The reason the histogram is not for visualization only, is for data reduction.
Yeah, yeah. No, I
Okay,
understand what you mean.
now, so it will be nice if we can plot to find the type of the Gaussian and to see how meaningful looks all the data of the normal distribution, not Gaussian, okay, of the
Okay,
normal
yeah.
distribution, and see which data you can use. I'm trying simply to say we may find some further reduction of the data.
Hmm.
You know what I mean?
Yes.
Okay. Also, I notice the data set is again, where did you get the data set? Again from simulation?
Yeah, the data set was from a simulation.
From simulation. Okay. So, in terms of machine learning, there is, okay. Okay, this is an excellent project, integrative. You have to highlight in your report that you involve a lot of components inside, in terms of software, in terms of machine learning,
Yeah.
in terms, sensors, and so on. You have to write it to make it clear. Okay, guys? Complexity, the project. So try to emphasize the 5 points that I told you at the beginning, every team. Congratulations, very good work.
Thank you.
Thank you.
Thank you very much.
Any other questions? Okay, thank you, Andrew. Thank you, Jack, and also Michael. Great job. I would like also to thank the